Hi everyone, this video is going to focus on predicting or determining the position of equilibrium in acid-base reactions and using a quantitative analysis, okay, which means we will be using Ka and pKa values to determine the position of equilibrium. Is an acid-base reaction favored in the forward direction or is it favored in the backward direction? So let's go ahead and get started, and we will basically cover this material using a few examples. Uh, so let's say we have an acid-base reaction where we've got sodium ethoxide. This is sodium ethoxide, 2 carbon, and then 2 carbons, and then an oxygen with a negative charge on it. Okay? And plus, we have acetic acid. In fact, I'm going to write or draw out that bond because we will be using that bond in our acid-base reaction. So looking at the two molecules here, and this is again acetic acid. Now, you do not need to memorize any of these things, like the names or like the compounds. The structure would always be given to you. But looking at the two structures, there's one with a negative charge on the oxygen, the other molecule is pretty neutral. So that suggests that this must be the base. So what I'm going to do is I'm going to use the lone pairs on this oxygen to go and abstract that proton, the acidic proton, in in our acetic acid. Now, why is that the acidic proton here? We will see that in the qualitative analysis later. Okay, but right now, a hydrogen or a proton that's connected to an electronegative element, like an oxygen or a nitrogen, that's more likely the acidic proton, the proton with a del positive. So that abstracts that proton. Electrons from there go to this oxygen, and what that means is we get products. Now, I'm not going to put the arrow here because that is the purpose of this activity. That is what we're trying to do here. Okay, so I'm just going to draw the structure of the products that I will get. So when acetic acid loses that proton, I'll get O minus. Okay, that oxygen is a minus now, and sodium ion, since it is just neutralizing the charge, that would be with that molecule, the species now. Okay, so that is, this is the acid, so that is the conjugate base now. And then 2 carbons, and then the oxygen, it abstracts a proton. So that means what I get is 2 carbons and now a hydroxyl group. Okay, I get a hydroxyl group. So these are our products, the two products that we get. So now, if we assign acid-base nomenclature to these, base, acid, when the base accepts a proton, it will become a conjugate acid, and the acid, when it loses its proton, it will become the conjugate base. Okay, so that is what we've got here. Now, pKa values. pKa values will be provided in an example or in a question for a problem like this. pKa values will be provided to you. So pKa values apply to acids. So you look at the acid, this acid, pKa value is around 4.75. Okay, so we'll just say that pKa value. pKa value for the other acid, now on the product side. So we have one acid on the reactant side, there is one acid on the product side. So the pKa value for the acid on the reactant side is 4.75. pKa value for this molecule, this is around 16. Okay, that's the acid on the product side. The other molecule is a base. So we'll not talk about a pKa value for that. But now we have the reactant side and we have the product side, and we have two pKa values. Now, based on this pKa value, we should be able to predict which of these two acids is the stronger acid. So the way pKa works, just as a review, this is a lower pKa, which means this is a stronger acid. This is higher pKa, which means this is a weaker acid. Okay, so we have the stronger acid on our reactant side, and we have a weaker acid on the product side. Now, in an acid-base reaction, okay, actually there's more. So this is the stronger acid. So going back to basicity. So if this is the stronger acid, then its conjugate base is going to be a weak base. So this is the weaker base now. Okay. And similarly, if this is the weaker acid, then its conjugate base. Now, what would be its conjugate base? Its conjugate base would be what is obtained by losing that proton, which is the molecule here. So, since this is a weaker acid, its conjugate base, which is this molecule here, would be a stronger. Okay? These are all relative terms. So this would be a stronger base now. So now if you look at it, on the reactant side, we have stronger base, stronger acid. On the product side, we have the weaker acid and the weaker base. Now, the way acid-base reactions work, okay, acid-base reactions favor weaker acid and weaker base at equilibrium. And what that means is these are present in higher concentrations, or these are formed. That is what I'm saying, okay? So in an acid-base reaction, the weaker acid and the weaker base are favored. So when you reach equilibrium, there's going to be more of those. So if there's more of those, that means the reaction is actually favored in that direction. So for this particular acid-base reaction, based on pKa values, what we can say is the reaction is favored in the forward direction, because that's where the weaker acid and the weaker base is. And no, sorry, this does not mean that the reaction does not happen in the backward direction. It's just less favored. So the way we show that is by using a smaller arrow pointing backwards. And so the way we read this is, this reaction is favored in the forward direction, less favored, or more favored in the forward direction, less favored in the backward direction. And that's because our stronger acid and stronger base are on the left-hand side, the weaker acid and weaker base are on the right-hand side. Okay, so let's do another example just to make sure that we've talked about all of this again. Okay, let's go ahead to another example. And this work that we do, it is a function of the acid and the base. Okay, do not try to memorize that a certain combination gives, or a combination would work, or a certain base is stronger, or a certain acid is stronger. That is not the case here. Okay. So let's look at another example here. So let's say we're looking at this carbon-hydrogen bond. So I've drawn out a hydrogen. So I'm specifically saying this is the carbon-hydrogen bond that we're going to focus on. And plus we have Na, NH2. Okay, this is Na plus and NH2 minus. So again, we have, because this has the negative charge, I think we're going to default to calling it the base, then this must be the acid. And since I have drawn out a hydrogen, now this is just an alkane. This has several carbon-hydrogen bonds. We're going for one carbon-hydrogen bond. That is what we're doing here, okay? So the base will come and abstract the proton. Electrons from this bond go to that carbon. There are 3 carbons in this molecule. 1, 2, 3. There is no carbon here because I have drawn a hydrogen over there. So this is a 3-carbon molecule where a hydrogen is drawn out. And the purpose of drawing that hydrogen out is because I want to show this electron movement. And if you go back, you would notice that every time I'm doing something with a bond, I am drawing it out because I want to show that electron movement. That is key, please. So do that whenever you're doing this. Okay, so now we're going to finish off. So this is the acid. It is losing the proton, so 3 carbons, lone pair there. So that means what I get at the end of this must be something like that. 3 carbons with a negative charge on that carbon. Sodium is balancing the charge. So the sodium is now here. Now, do not also think that you have to write the sodium down or below this charge. I'm just doing it for the lack of space because I realized that that's how I wrote it a couple of times. So please, I'm not following any conventions here. You can just write the sodium right here, okay? But maybe I'll just move it up here because I think I should have enough space in this example, okay? So NH2 minus grabs a proton, abstracts a proton, which would give us NH3. And nitrogen has 1 lone pair now. So acid, base. Acid, after it loses its proton, would give us the conjugate base. Base, once it accepts the proton, would give us the conjugate acid. Okay. And again, in this particular case, pKa, okay, because we are doing a quantitative analysis to predict the position of the given, pKa's would be given. pKa for the acid on the reactant side is around 50. Okay. pKa for the acid on the product side. Again, we were not talking about pKa's for the base or the conjugate base, but pKa for the acid on the product side, this is around 36, let's say. It's somewhere between 30, I think that is a good number, okay? Like, to a good approximation, that's fine. So 36. So, based on these 2 pKa values, we have lower pKa here, which means this is the stronger acid, and this is the higher pKa, which means this is the weaker acid. So low pKa means strong acid, high pKa means weaker acid. Now, since we have the stronger acid over there, its conjugate base, which is this minus a proton, is this molecule, okay, that must be a weaker base because this is the conjugate base of a stronger acid or a strong acid relatively. Okay? The acid is strong, so the conjugate base is going to be weaker. Now, please do not confuse that I've written base here and I'm calling it a conjugate base. This is the conjugate base of that acid because conjugate base is obtained by the loss of a proton from an acid. So when NH3 loses a proton, this is what I will get. So that's the conjugate base. So stronger acid, weaker base. Weaker acid, that means this is the relatively stronger base. So now that we've done this, what we notice is the strong acid and the strong base are on the product side, the weak acid and the weak base are on the reactant side, and at equilibrium, acid-base reactions, they favor the weaker acid and the weak base. And so that means this reaction is actually favored in the backward direction, and it will go extent in the forward direction. So again, that's how we read those arrows. This is favored in the backward direction. But we don't have to write this. That is how these arrows are read. The arrows of unequal length, when it is like longer pointing back, means it is favored in the backward direction, or the reactants are more favored. And that's because this is where the weak acid and weak base is. So I hope that's helpful, and with that information and the similar analysis, you should be able to attempt problems like this, which deal with a quantitative analysis. Now, the reason we're calling it a quantitative analysis is because we have pKa values to look at, and we derive or we arrive at conclusions based on those pKa values. Now, in the next section, we are going to talk about qualitative analysis. That means, how do you assess acid strengths when pKa values are not given? Because there are so many organic molecules. Not every organic, I mean, you cannot come, and you can, but you will not have pKa values for like all organic molecules in a table. So we need to do this qualitatively. So that is where we are going